Have you ever just stopped and wondered what holds our world together? I mean, literally. There are these invisible forces constantly pulling and pushing on everything we build, from a simple chair to the most massive skyscraper. So the real question is, how on earth do engineers predict and control these forces? To really get it, let's look at a structure where the stakes are about as high as they can get. Just look at this oil rig. Every single piece of that steel, especially those super long drill pipes going deep into the ground, is being stretched and squeezed with absolutely incredible force. If an engineer's calculation is off by just a little bit, well, the result could be a disaster. So how do they nail it every single time? How do you predict the behavior of something you can't even see? Well, to understand their secret, we first have to zoom in and understand the fundamental problem that comes with stretching any material. It really all boils down to two key concepts: stress and strain. Okay, think about it like this. You pull on a rubber band, right? That pulling is the load. Well, stress is the invisible internal force inside the rubber band that's fighting back against your pull. And strain? That's the result you can actually see. It's the stretch, the deformation. But here's where it gets messy in the real world. You see how the grid lines on this bar get all warped and weird near the ends where the force is being applied? The stress and strain there aren't nice and even. It's a localized, super complex mess. Trying to calculate this mess for every single part would be, well, pretty much impossible. So what's an engineer to do? Well, they have a brilliant little secret, a kind of shortcut that makes the impossible, well, possible. It's called Venant's principle, and honestly, it's a total lifesaver for engineers. All it really says is that the messy, complicated stresses you see right at the ends, it doesn't really matter once you move a little bit away from them. The effects just kind of even out. They fade away. And this visualizes it perfectly. Look at the image on the left. That's near the load, and you can see the stress is all over the place. It's chaotic. But now look at the right. A little further down that same bar, the stress has almost magically smoothed itself out into this beautiful, uniform, and, this is the most important part, predictable pattern. And that is the whole game changer. St. Venant's principle basically gives engineers permission to ignore the super complex stuff happening at the connections and instead focus on the much simpler, much more predictable stress in the middle of the part. This is the key that unlocks everything. Okay, so now that we have a way to simplify the problem, how do we turn that into a rock-solid prediction? You guessed it, with a really powerful formula. And here it is. This is the equation for elastic displacement. I know it looks simple, but this little formula is the powerhouse tool engineers use to calculate exactly how much something is going to stretch or compress. We say it as delta equals NL over AE. Let's just quickly break it down. That little triangle, delta, that's what we're solving for, the total stretch. N is the internal force, the pull or the push. L is the object's original length. A is its cross-sectional area, how thick it is. And E is the modulus of elasticity. That's just a special number for every material that tells us how stiff it is. Steel has a crazy high E, a rubber band a very low one. But you might be thinking, what if you have a complex object, like a bar made of different pieces with different forces pushing and pulling on it? No problem at all. The formula is awesome because you just calculate the stretch for each individual piece, and then you just add them all up. Simple as that. All right, enough with the theory. Let's see how engineers actually put these numbers to work in a real scenario. So the process is actually very methodical. It's a two-step dance. First, you figure out the internal force. That's our N for every single section of the object. Then, once you have all those forces, you just plug them into our trusty formula, calculate the stretch for each piece, and add it all together. So check this out. It's a classic problem. We've got this steel bar, it's fixed on one end, and it's being pushed and pulled by 3 different forces. The big question is, does the whole thing get longer or shorter in the end, and by exactly how much? So, step 1, we find those internal forces. Using what's called the method of sections, which is like taking an imaginary slice through the bar, engineers can figure out exactly what's happening inside. They can see that some parts are being squeezed, that's compression, while other parts are being pulled apart, that's tension. And now for step 2, the payoff. We apply our formula to each of those segments. You can see it right here in the table. We plug in the force, the length, the area, and that stiffness number for steel for each section. Now notice the signs. A negative force gives us a negative displacement. That means it gets shorter. A positive force means it gets longer. Then all we have to do is sum it all up. And there's our answer. The total change in length is negative 0.891 millimeters. So even though one section was being pulled apart, the forces pushing it together were stronger, and the entire bar actually got just under a millimeter shorter. I mean, that is the incredible power of predictive engineering.
So why does all this matter? I mean, beyond just solving problems in a textbook. What's the big deal?
Well, it matters because this is what engineering is all about. It's taking a really complex, messy reality, applying a clever simplifying principle like St. Venant's, and then using a powerful formula to make an unbelievably precise prediction. This whole process is what lets us build a safe and reliable world.
So let's just recap the big takeaways, right? Stress is the force fighting back inside. Strain is the stretch you can see. St. Fernand's principle is our get-out-of-jail-free card that lets us ignore the messy ends. With that simplification, the formula, delta L over AE, gives us predictive superpowers. And this is the fundamental math that makes sure our bridges, our planes, and yeah, our oil rigs actually work.
Which, of course, leads to a final, pretty critical question. We've figured out how to predict how much things stretch when you put a load on them. But what happens if you just keep adding more and more and more load? If we can predict the stretch, can we also predict the exact moment something will snap? Now that is a question for another time.